Hello, ladies and gentlemen. It's 5 p.m. Central European Standard Time, and I guess it's time to kick things off. So, hello everyone, and welcome to the SimScale webinar. I'm your host and moderator for today's session, Yusuf Murad, and I'm a product marketing engineer here at SimScale. It's really a pleasure to host this webinar today, most importantly because I have an expert on my side, namely my colleague David Short, who is an application engineer here at SimScale. He will also introduce you to the platform and how to set up a battery pack gap filler simulation using our Thermo-mechanical module. Just as a side note, at the end of this webinar, we will have some time to cover all your questions in a dedicated 10 to 15 minute Q&A session. So if you have any questions about the webinar, today's case study, or SimScale in general, please put them in the little chat box or little Q&A box, and we will make sure to take them one by one at the end. Okay, let us have a quick look at today's agenda. Today, we will be demonstrating, as already announced, the benefits of engineering simulation in the cloud and how you can use the Thermo-mechanical module inside of our platform for battery pack simulation studies. In general, gap fillers can outperform thermal pads in battery pack applications to achieve lower thermal impedance, as the gap fillers basically conform to surface roughness before curing. And more importantly, different materials result in different mechanical performance, which we can post-process in form of such as the casing stresses of pouch cell swelling, but also performance differences due to drastic temperature gradients inside of the cells. And my colleague David will later on show you how this will look like in terms of post-processing. Okay, some of you might know what SimScale is all about. A lot of you are new here. So let me briefly introduce what SimScale is all about. So in general, we see many engineers and designers new to SimScale who are very curious to learn what we are all about. So our main idea or the main focus is that we are committed to making engineering simulation more accessible, whether it's from thermal, structural, and fluid simulations, to also other industries who couldn't afford simulation so far, especially on the cloud. And we strive to introduce so-called digital prototyping into any R&D cycle. That means we can explore the full design space with a desired accuracy, but also reduce trial and error, which usually comes with physical prototyping. To summarize all of this, we are basically focused on delivering computational resources that scale up on demand. That means whenever you need them. We offer streamlined simulation workflows, but also offer modern sharing and collaboration features. And our dream is that every engineer and designer is able to simulate early, simulate more, and especially simulate now. Or to say it even more crisp, which is our mantra, is you come with your CAD model and basically leave with a design decision. Okay, a little bit of a repetition of what we're actually doing at SimScale. So when it comes to the power of the cloud, I already alluded to the on-demand capabilities of SimScale, which means what we usually see is that once you buy a very powerful working station, which we still see, especially still in the age of the cloud or in cloud computing, you buy these powerful workstations. Sometimes you don't even need the full power of these workstations. So that means even if you have a simulation which doesn't need so many CPUs to run on, or even a bigger machine. So you can basically scale up or use as many cores as you want, depending on your needs or simulation needs, basically. Also, what I mentioned is to explore your full design space. That mentions you can run different scenarios, so-called what-if scenarios. You can assign different boundary conditions to your case, start the run, and basically post-process runs that already have been performed, which already brings us to the last point, which is you can get accurate simulation insights in real time. That means everything from pre-processing, processing, but also post-processing can be performed inside of the browser, which I think is a really, really nice feature. When it comes to the technically and economically accessibility, basically when you use the cloud, you can drastically reduce operational overhead. So all the IT complexity, such as node handling and other bits and pieces that you don't want to deal with as an engineer or designer, are taken by SimScale and packed into one single SaaS application. So you don't have to worry about any coding or things like that. You just use the interface and basically can kick off your simulation studies. Also, cloud HPC availability 24/7, and if needed, you can share your simulations inside of your team or even remotely if you want to give people access to your simulations. What we are very, very proud of is the in-product support. That means if you have any problems using the platform at any given time, you can use our chat functionality, and my colleagues will be more than happy to help you out. And last but not least, you can basically build simulations very quickly, and as already alluded to, post-process everything in real time. That means you can run tens and even hundreds of simulations in parallel. And once you're done with one simulation batch, basically, you can post-process them, have design insights, and basically iterate quickly. So with that, I already hand over to my colleague David, who will introduce you to the case study today.
So thanks very much for that. Now I'm going to take you through the technical side of this webinar, where we're going to be looking at battery design, both with elements of thermal management and mechanical performance as well. So the project that we'll look at is assessing a battery pack assembly, which has a couple of cooling plates, pouch cells, insulator pads, as well as gap filler material. And that's really going to be the focus of today's webinar. So we've got our geometry, 3D solid body geometry, and you can use whichever tool you like for that. I'm myself using Onshape, and I'll show you that in the demonstration as well once we get onto the platform. We then need to create our simulation model. Like with all of our simulations, that involves creating a mesh, and we're using automatic meshing for this project. The physics we'll look at today is a thermo-mechanical analysis, so bringing in thermal stresses into a conduction-based simulation. We're going to solve, as always, with our cloud-native solution, and with giving us the ability to identify the temperature hotspots as well as those peak mechanical stresses and deformations to understand how is our module performing both thermally as well as mechanically. So here's a little bit more detail about the scope of the project and the model that we'll be running. So the battery pack consists of 4 modules. It's a lithium-ion battery pack for EV, electric vehicles, and yeah, we're going to be looking at the thermal management of this battery module. So as I mentioned earlier, we've got 2 water cooling plates on the top and bottom of the battery module, and separating the cooling plates from the pouch cells and the casing itself is actually a gap filler material. Now gap fillers are critical for a number of reasons. So they need to provide electric insulation, they need to provide vibration damping, as well as the ability to actually conduct the heat across the interface between the battery packs and the cooling plates. So to make sure that we actually utilize the cooling capacity of our cooling plates, we need to make sure that we have an efficient gap filler material in the model. And that's what we'll look at today, is actually optimizing the gap filler selection, as well as looking at optimizing the thickness of the gap filler as well. So the analysis type we use is a thermomechanical analysis, so a multi-physics application where it's both thermal analysis and mechanical stress analysis. And yeah, let's get into it. Let's see some of the design insights that we get out of this kind of analysis, and then I'm going to jump right away into the platform so I can show you around SimScale, give you a bit of an insight into what we're doing as a company, and hopefully spark some interest. And yeah, so if you've got any questions, please do write those into the chat, and we'll answer those at the end of the session. So if we take a look at some of the insights that we can extract from SimScale design studies, I've initially run 3 different gap filler materials, each with the same thickness. So I've got my 3 different gap filler materials with 2mm thickness. But obviously these materials have different conductivity values. So I first wanted to have a look at what is the effect of just using a different gap filler material selection in terms of the maximum cell temperatures that you see in the pouch cells, as well as the amount of mechanical swelling due to those temperatures in the pouch cells themselves. So we can see that I've arranged them in ascending order of conductivity, and with that increased conductivity we then see a reduced maximum cell temperature. Now it's fairly minor because we're having a fairly dominant effect of the water cooling plates here, but still we see the trend in Increasing the conductivity of the gap filler material is thus reducing the maximum cell temperatures throughout the pouch cells. And that can have a bearing on designs as well as costs in manufacturing as well. So if we have optimal selection of gap filler materials, it could mean that we could have a more efficient or a less energy intensive cooling apparatus on the cooling side of the battery cells here. Obviously, we have to have some kind of cooling capacity. We have to have some kind of gap filler material, and then SimScale allows us to then actually optimize that selection. So we see an decreasing maximum cell temperature, decreasing pouch cell principal strain, which is an indication of the actual volumetric swelling of those cells. And then I've put some visualizations of the temperature distribution across both the pouch cell surfaces, right in the middle of the module. As you can see here, my mid plane comes through the center of the module. So we can see that we have obviously higher peak temperatures on the left hand side where we're using the gap filler material with low conductivity, and then when we go over to a high conductivity material, we have both lower temperatures and more uniform temperature distribution as well, which is obviously critical as well for battery design. We want to make sure that our cooling capacity is being utilized across the whole module uniformly, so that we're not going to have some hot spots and some cold spots. We want to have optimal performance out of all of the cells in the model. I've also done a cutting plane on the gap filler materials themselves, and we see the same distribution or the same trend here. Now, moving on from just the gap filler material selection itself, we can use SimScale to optimize the actual thickness of the material and or understand what bearing does the gap filler material thickness have on the actual temperature distributions and thus the mechanical thermal strains as well within the system. So as we increase the thickness, I'm going from a 1 millimeter to a 3 millimeter thick gap filler material, we actually see the reverse effect. So with a thicker gap filler material, we actually have higher pouch cell temperatures, and that's because we're reducing the effectiveness of the water cooling plates. Okay, so really we want to try and keep the gap filler material as thin as possible, but obviously we need that gap filler material for vibration damping and for insulation as well. So it's going to be a balancing act, but SimScale obviously gives you the ability to dig into those physical behaviors and understand what is causing the hot spots and how can we mitigate them. Finally, what we can get out of this same simulation is the mechanical performance as well. So I've got just looking at the same gap filler material here, the lowest conductivity gap filler material with the lowest thickness as well. Here we can see the actual mechanical stress in the steel casing around the battery models itself, and that's where we're seeing the maximum mechanical stress, and we're even getting to the point of yielding here. So in this joint section here, we have some mechanical stress going up into and above the material's yield stress. So in those regions where we have significant stress going above yielding, we could be expecting then to see some damage, some plastic deformation, and this is then the first insight to say, oh, okay, let's think about maybe resizing the casing thickness. Let's think about maybe using a different, more ductile material for the casing to reduce those mechanical stresses and thus increase the lifetime of the product. Now, I've run this as a linear static analysis for the mechanical part. So we're only identifying where do we have areas above yield. If we want to go into further detail, then we can convert this to a non-linear simulation, bring in some non-linear material properties as well, and then really see what are the absolute maximum stresses that we would experience during this thermal cycling of the battery module. The same goes for the total strain in the pouch cells. So I've visualized here the total strain in the pouch cells, and we can see that we have roughly 1 to 2 percent of total strain magnitude in the pouch cells themselves, and that's really only due to the thermal stress. Obviously in battery design, you also have chemical reactions and things like this, but it's important to understand that it's not only the chemical reactions that could cause swelling of battery cells, but also the thermal behavior as well. So without further ado, I now want to bring SimScale into the picture so that I can show you around and we can see this in action. So here comes SimScale. The first thing you'll notice is it is purely contained within a web browser. So that comes with it a couple of major advantages. It means it can be accessed from anywhere at any time. And because it has no footprint on your local hardware, and we're not going to run these simulations on your local hardware, it can also be accessed at any scale. So if you've got a very complex design, then it will run on a larger machine. If you've got a simple design, it will run on a smaller machine. Okay. So we're looking at some of those results that we've already discussed. I've got the actual temperature distribution on the bodies themselves, and I've also got an ISO volume showing us where do we have those high levels of mechanical stress within the model. And yeah, so let me show you how we get to this point. When we come into SimScale, the first thing you're going to be doing is uploading your geometries. So you can bring them in from any CAD tool, and I'll show you this in action in just a moment's time. So once you have your geometry, or as many different design candidates as you like in the SimScale project, and there's no limit on the number of models that you can have, then you can create your simulation. So let's go to create simulation. And you see our simulation library. So we do fluid flow analyses, structural analysis, and some multi-physics type analyses as well. So we've got thermo-mechanical, and we can go create simulation. Now, with all of our simulation templates, it guides you on your way to successful simulation. So it already has a checklist of the things that need to get done before your simulation is ready to go. A lot of that is taken care of by SimScale's default settings, and a lot of the setup operations are also taken care of automatically. So one thing you already just saw is it automatically found the contacts within the model. So it went through and found all the different contacts within the model to firstly glue the model together. It's a large assembly here, as well as enable heat transfer across those contacts as well. So those are bonded and thermal coupled contacts by default. So then the only thing you really need to consider is the design parameters, the materials, as well as the operating conditions, the boundary conditions. Everything else will be run on the SimScale defaults. But obviously, if you're a simulation expert and analyst type, then you can go in and you can customize any of the defaults that we're using here to run our simulations. And you can have full control over meshing strategies, numerics, as well as the full workflow. So let's have a look at the one we've already prepared. So we've got our webinar thermo-mechanical simulation here, where I have applied materials to the pouch cells, to the insulation pads. I've used some from our default material library, and I've used some custom materials as well. Okay, we've got aluminium in the battery pack case, and our water cooling plates are these steel channels on the top here. Okay. To actually model the physics of the gap filler, we have inserted 3 different gap filler materials, and then they can be selected or deselected and applied to the actual volume. And I'll show you how we can set off a number of different simulations with different gap filler materials, so that then we can find the optimal selection. In terms of operating conditions themselves, we're fixing the top surfaces of the structure, and then we're applying a convective heat flux on the water channel surfaces. So in here, rather than running a full conjugate heat transfer CFD simulation, we're just simplifying the case by using a convective heat flux boundary condition on those water channels, so to bring in the effect of the water cooling, because we're not really optimizing the water cooling plates here. We're having a look at the effect of gap filler materials on the thermal management and the thermal behavior and mechanical stress within the model. I'm using volume loads to apply the actual wattage to the battery cells themselves, and I'm applying an ambient convective heat flux onto the external surfaces as well. So let's set off a few different simulations. So in terms of the geometry I'm using, I've got here my 3mm gap filler model, so we can keep to that, and we've got the Saint-Gobain, the TC 2006 gap filler material, but let's switch that out. So let's use a different gap filler material. Let's use Henkel, and I would apply that then to the gap filler topology set that I've created over here. Okay, so then we can go and start our simulation, and we can call that 3mm Henkel 1500 LV. Okay, so we can start that simulation there. Now, unlike local hardware, we don't need to wait for that simulation to finish before we can keep going and work through. So let's go back and change the gap filler material again. And let's go with the TC 3008 and start off a new simulation here. So we can go 3mm, that's the TC 3008. Okay, and those simulations were set off there. You saw it gave us a little estimation of how long it will take. We'll have a look at that when we set off our next simulation as well. So not only can we change the operating conditions or the material selection, we can also change the geometry as well. So let's go for our 2mm model. So we've switched the geometry and now our gap fill is much thinner, or we can go to the 1mm, even thinner. Let's hit select there, and then we're going to redefine our contacts automatically, and then we can go through and start the next simulation. So now we have our 1mm model, 1mm model, and that is the TC 3008. Okay, so that's what it looks like playing around with SimScale. So it gives you the ability to test out multiple different design variables in a short space of time. Now, I really want to show you maybe start to finish how you can work from a CAD tool as well to bring these kind of designs in and make an additional design variant. Say, hey, let's go for an even thicker part, for example. I can show you this in just a second. So I will bring in my Onshape model now. So Onshape is another cloud-based tool, so it pairs up really, really nicely with SimScale, which means that you can have your whole CAD system and your whole simulation system cloud native, meaning that obviously accessible from anywhere at any time, at any scale, and we can then play around with the CAD model so that we can test out some additional features. Now, I have parameterized this model just slightly to enable quick changes to the gap filler thickness. So if, for example, I go in here and go 4mm on my gap filler, it will then update the model, providing us an even bigger gap filler material in here. Okay. I'm not going to go through the CAD creation itself, but I just want to mention that we have I've used a quick parameterized variable here to allow for quick design studies. Now, with more complex models, you might want to parameterize the number of pouch cells, for example, the water cooling channel spacing. Really, the possibilities are endless in terms of actually producing these design-based studies. Now we've got our 4mm gap filler material here, so let's create a version and we'll call it gap filler 4mm. We create that version and then we can go back to SimScale and bring in our new geometry. So let's import from Onshape. So we've got a direct integration with Onshape. Search for our model and then go to the versions, and we can get our version 4, which is the 4mm gap filler material. Okay, so let's import version 4, and we'll let that load into the SimScale project. And yeah, I just wanted to mention that the reason why we're able to do this with Onshape and with any tool is the fact that we have CAD associativity using named selections. So when you bring in models from whichever tools you like, you can make them associative with your simulations by naming the parts accordingly. So just create a group or create a name on specific faces for the gap fillers, for the plating, for the pouch cells, for example. And then this enables us to switch between geometries without the need to set up new simulations. So then we can see our new model has come in with the topology entity sets correctly, and our new 4mm ridiculously big gap filler material. And then we can use that as an additional simulation. So let's go back to our design study here, and we can switch on to our new model that we've just brought in from Onshape. And there we go. So it's found its contacts, and we are ready to rumble. So we call that 4mm. That's the TC 3008. Okay. So then we've got 4 simulations all running in parallel, so they'll all come back at roughly the same time. A simulation like this, let's have a look, takes about 36 minutes to complete. It's quite a heavy model because the number of degrees of freedom we actually have for this finite element analysis. So we've got 420,000 nodes. Obviously times that by 3 to give us the actual number of degrees of freedom. So it's a large system matrix, and so it's going to run on a fairly large machine and give us that kind of runtime for this kind of analysis. Okay, so hopefully that gives you a bit of a reference point on what you can achieve with SimScale, what kind of physics that we specialize in, as well as how you could implement simulation into your design processes to give yourselves more insight compared to prototyping, and actually save costs as well on prototyping studies. Okay, well, I will hand back over now. Thank you very much for listening, and if you have any questions, then we will make sure to answer them.
Thank you so much, David, for this great live demo. As for the next steps, before we jump straight to the Q&A session, if you have any questions or want to request a demo, feel free to reach out to our sales team by contacting us directly at sales@simscale.com, and an application engineer will get back to you and help you out with your simulation studies. Cool. Now, with that being said, we can kick off the Q&A session. If you have any questions, as I already mentioned, put them in the Q&A box and we will take them now. Great. So the first question coming in is about tetrahedral meshes. Is this a tetrahedral mesh that you were using here, David?
Yes, yes, you're right. This is a tetrahedral mesh. So in terms of the mesh elements that we provide on SimScale, we provide first order and second order tetrahedral elements. So we use a really robust mesher, which starts off as a triangular surface-based mesh, so making it really handy at capturing complex geometry, and then it will build tetrahedral elements out from that triangular surface-based mesh. So it makes it pretty robust, and it makes automatic meshing actually pretty yeah, all that we need to do. So I generally use automatic meshing about 80% of the time, but with any of our automatic algorithms or meshing strategies, you can add your own manual refinements on top of that. You can control the sizing manually as well. But generally, I find automatic meshing certainly does the job on the FEA side.
Mm-hmm. Excellent. Thanks, David. There was also a question on the boundary conditions. I think you went into that even deep in the demo, but do you want to add your 2 cents here on boundary conditions in general?
Boundary conditions in general, I can do. In terms of this analysis, because it's a thermo-mechanical analysis, obviously we need to have boundary conditions that are constraining both the stress side of things. So we need to make sure we don't have an unconstrained body. We need to fix it somewhere, add some constraint, but we also need to apply those thermal boundary conditions. And the way we can do that is either through volumetric heat sources, so giving some wattage to specific volumes. We can add surface-based heat fluxes, for example, for modeling the ambient natural convection effects, for example, like we've done in this model. So there's surface-based boundary conditions. There's also volumetric boundary conditions. Yeah, I think that's probably all I need to talk about in terms of boundary conditions. If you've got some more specific questions about one of your own problems, then we can definitely dive into that in a one-on-one session. So give us a call, and we can help you out there.
Cool. Thanks, David. About the mesh again, do you think a hexahedron mesh would be better for this type of application?
So hexahedral meshes are good in simple cases, I find. So if you have the ability, if you have square bodies, then hexahedral can be beneficial in terms of accuracy. It could be beneficial, but we don't have hexahedral elements on SimScale currently. We're developing large shell elements as well, so that should also help in these kind of applications. But at the moment, we're limited to tetrahedral elements. But you might be right, because we've got such a rectangular based body. I think hexahedral elements could bring some advantages here.
Mm-hmm. Great. Also a question about digital twins. Does SimScale allow for the development of digital twins?
Well, absolutely. So obviously, digital twins is a big buzzword in the industry at the moment, and we do a lot of work here as well, because we have a simulation platform that has a large spread of analysis types and capabilities, but it also has the ability to run in the cloud and be accessed via an API. So it can be scripted, it can be programmed, allowing it to be integrated into digital twin systems. So we do a lot of work in terms of automotive component design and things like this, where we can actually be scripting parametric-based studies and bringing that into the sort of world of digital twin. Now, I don't know what your definition of digital twin is. Every person I talk to has a different opinion on this, but in terms of having accessible simulation that can be run from anywhere at any time, then SimScale provides a really good basis to be able to be used in a digital twin. So it doesn't have to be running on local hardware or something like this. And because we've enabled API access, so you can script SimScale operations, that allows it to be integrated into digital twin type scenarios.
Great, I think that covers it. And the last question we have coming in is if real-world data can be basically considered in our simulation. So basically imported into the SimScale platform and then setting up a simulation. So
there's obviously the material data, for example, needs to be influenced by experimental data, for example. So if you're using nonlinear material, so you've got a nonlinear stress strain curve, that will have to have been produced from experimental data. We've got a lot of defaults that obviously come from that experimental data as well, but there's a lot of ways we can implement experimental data. For example, when we model electronics components, rather than modeling the full component, you can model thermal resistance networks based off experimental data of those single components to make your simulations a little bit more efficient. But yeah, in terms of other experimental data, it's a shame. I'd like to have a proper conversation with you, because that's an interesting question, and I'm not quite sure where what you're trying to get at fully there. So yeah, again, give us a call, because that'd be a really interesting conversation.
Cool, thanks, David. A very interesting question, because you used the thermo-mechanical module here of SimScale. Another question we have coming in is about forced and natural convection. Can we model things such as fans, heat sinks, things like that?
Absolutely. So my CFD colleagues will be very happy that you've asked that question, because that brings you into the world of CFD. So bringing together both the internal thermal conductivity in your solid bodies, but also bringing in that convective behavior in the air. So to be able to simulate the active cooling explicitly or the passive cooling explicitly, that is going to require a coupled CFD analysis. And that is absolutely something that we offer in our conjugate heat transfer simulations. So if you need to do some passive cooling or active cooling on for example, LED devices, or battery packs that are actively cooled, this this application here could also have been run using a conjugate heat transfer simulation where we simulate explicitly the fluid flow through those cooling plates, through those water cooling plates. I didn't bother doing that because I was only interested really in the gap filler behavior, and I was happy approximating the cooling capacity of those water channels. But absolutely, using conjugate heat transfer simulations is where you want to go in terms of thermal management situations where you've got active and passive cooling applications.
Excellent, David. I think that covers it with the questions so far. We have no more questions coming in. If you would like to see me and David maybe next week in another mechanical webinar, make sure to sign up and check out other webinars at simscale.com/webinars-workshops. We have a lot more coming up in terms of CFD, FEA, also thermo-mechanical simulation if you're interested in pump design, things like that. So make sure to check it out. If you have any questions regarding this webinar, it will be available on demand on our channels. And yeah, hope you enjoyed the webinar and have a nice evening, day from wherever you're watching this webinar right now, and I'll see you in the next webinar. Thanks, David.
Thank you very much, everybody. Bye-bye.